Welcome to the deep dive. We've got quite the stack of research you sent our way, and it looks like we're diving deep into the forces that have shaped and continue to shape our world, everything from, asteroid impacts to the formation of the Great Lakes. So you want to get up to speed quickly, but also really understand what these scientists are saying, and our job is to kind of pull out the most surprising, the most important insights from all this material.
Yeah, I mean, what you sent, it really highlights how Earth is this constantly changing place. You've got cosmic events, and then at the same time, you have these incredible, slow-moving geological forces, and it's all connected, all fascinating, and we've got some really great scientific research to dive into.
Okay, so let's start with something, well, kind of terrifying. Asteroid impacts. I mean, it's not just a Hollywood thing, right? Like Armageddon or something. Your research paints a picture of Earth being bombarded.
Yeah, it's definitely not just science fiction. I mean, the really big ones, the ones that could, wipe out civilization, they're thankfully super rare. Like we're talking once every 75 million years or so. But, smaller impacts, ones that could still be devastating, they happen much more often. It's a spectrum of risk, and we need to understand it.
And by smaller, we're still talking about pretty big events, right? I mean, one source mentioned an asteroid just 150 feet across could basically destroy a city like New York.
Yeah, it's sobering when you think about it. 150-foot asteroid, that's not even that big compared to some of the ones out there. While we can't predict exactly when or where, statistically, events like that are more likely than those civilization enders. And it all comes down to the sheer energy involved. When you've got an asteroid, say, weighing 100 billion tons, slamming into the Earth at tens of thousands of miles per hour, we're talking about an unbelievable amount of energy, hundreds of millions of nuclear explosions.
Wow. And it's not just theoretical, right? I mean, look at the Arizona Meteor Crater. That thing is enormous, nearly a mile wide, over 500 feet deep. And it was caused by an asteroid that was probably only around 130 feet across. It's hard to even picture that kind of impact.
Right, and that was about 50,000 years ago. That impact ejected 175 million tons of rock. I mean, it's a huge reminder, that even relatively small space rocks can leave behind a lot of damage.
And one of the researchers he sent, Professor Ted Bunch, he makes the point that Meteor Crater isn't just, some ancient event. It's a warning. We got to be prepared for these more frequent, smaller impacts. It makes you think about how vulnerable we are, floating around in space like this.
Absolutely. It's a reminder that we're constantly moving through this cosmic shooting gallery. I mean, imagine something like that hit a major city today. The initial impact creates these massive shock waves. Like, imagine a supersonic pressure wave radiating outwards, plus intense heat that would melt rock instantly.
So we're talking like total devastation.
Pretty much. For a city like New York, the estimates are pretty grim. Within a 5-mile radius, probably 80% of people would, suffer fatal injuries or death. It's the blast wave, the heat, buildings collapsing.
And it's the combination of like speed and mass that makes these impacts so destructive, right? That 50,000 miles per hour, that's just unbelievable.
Exactly. I mean, kinetic energy, it's related to the square of the velocity, so even a small increase in speed means a huge jump in destructive power. And, we find evidence of these impacts all over. These rocks that have been deformed, melted, scattered by the heat and pressure.
The stalactites, right?
Yeah, impactites, they're like the scars of these events. And they're not just cool rocks. They help us understand Earth's history, including possible links to mass extinctions.
And it's like a detective story, right? Putting together these clues. There's some research about woolly mammoth tusks in Alaska with these tiny meteorite fragments embedded in them. And it's possible that an impact, maybe 34,000 years ago, had something to do with these animals disappearing from that area.
Yeah, and there's other evidence, like, the Clovis people, they vanished around 13,000 years ago. And around that same time, there's this layer in the Earth called the black mat, and it indicates, like, massive fires and heat, a huge event. But the problem is, there's no obvious crater.
So could an impact be that destructive and not leave a crater?
Oh, that's where it gets interesting. Professor Peter Schultz, he does these experiments where he fires projectiles into ice to simulate asteroids hitting ice sheets. And what he's found is that even a relatively small asteroid, half a mile wide, if it hits an ice sheet, it could cause massive explosions and fires, but the evidence would melt away with the ice. It's like a perfect cosmic crime.
So it's kind of scary to think about all these mid-sized asteroids out there, and maybe they hit Earth and don't even leave a trace. And then there's the Tunguska Event in 1908, which that was an explosion over Siberia that was as powerful as 1,000 atom bombs. It flattened hundreds of square miles of forest, and again, no crater.
Yeah, Tunguska is a great example of what's called an airburst.
Hmm.
Early estimates thought it was caused by a huge asteroid, maybe up to 600 feet across. But Dr. Mark Boslow, he did some supercomputer simulations, and he thinks it was probably much smaller.
How much smaller?
Maybe as small as, 100 feet. So same size as the one that made the meteor crater. But instead of hitting the ground, it exploded high up in the atmosphere. And as it exploded, it kept moving, creating this massive shockwave that spread out. That's why the damage was so widespread.
And I guess what's concerning is that if an airburst that powerful can be caused by something that small, well, maybe these things happen a lot more often than we think.
Yeah, some scientists think they might happen every few hundred years. It's been over a century since Tunguska.
Okay, well, that's all pretty terrifying. But thankfully, there are people like, NASA's Space Guard Survey, right? They've been working since 1998 to find and track those really big asteroids, the ones that are over 3,000 feet across. And they found a lot of them.
Yeah, Space Guard is important. They're focused on the biggest threats. But there's this former Apollo astronaut, Rusty Schweickart, and he argues that we need to do more.
Like what?
Like, track the smaller asteroids, the ones that are 100, 150 feet and larger. They might not wipe out civilization, but they can still cause a lot of damage, and they're much more common.
It's like, insurance, right? You hope you never need it, but it's good to have. Speaking of close calls, there's the Apophis asteroid. Remember that? It was discovered in 2004, and there was a lot of concern that it might hit Earth in 2029.
Yeah, Apophis is about 900 feet across. Dr. Richard Binzel, he did some analysis, and he said that if it hit, it could cause devastation over an area the size of France.
Wow, so what's it made of?
It's mostly chondrite rock, which is a pretty common type of meteorite.
Hmm.
It's estimated to weigh something like 20 million tons.
Oh.
And if it hit, we're talking about a 375 megaton explosion.
I mean, that's a lot. Thankfully, it's not going to hit, right?
Thankfully, no. More recent observations have refined its trajectory, and it's going to miss us. In 2029, it'll pass within about 18,000 miles of Earth, which is still pretty close in cosmic terms.
Yeah, a little too close for comfort. So what if we did find an asteroid head straight for us? What could we do?
Well, there are a lot of ideas. Blowing it up with nukes, that's one option, but it's pretty risky. You can end up with, a bunch of radioactive asteroid chunks, which is, well, maybe not ideal. Dr. Massimiliano Vicile, he talks about that.
So what are some other options?
Well, there's the idea of attaching, like, rocket engines to it or solar sails to slowly nudge it off course.
Okay, so like a really slow, controlled push.
Right. And then there's the kinetic impactor idea, basically ramming a spacecraft into it to change its trajectory. That's the idea behind the DART mission and the proposed Don Quixote mission, which Chris Saunders at Kinetic Labs is working on.
I mean, I guess that makes sense. A little nudge now could mean a big miss later on. And then there's those sci-fi sounding solutions, like vaporizing part of the surface with lasers.
Yeah, Dr. Vassal has been doing experiments with lasers, and another idea is to use like giant space mirrors to focus sunlight onto the asteroid to kind of boil it away.
I mean, all that sounds pretty difficult.
Yeah, those are, big engineering challenges for sure. And that's why early detection is so important. Like, we need to know what's out there and where it's going. It's like insurance, Rusty Schweickart says. You hope you never need it, but it's better to be prepared.
It's a good point. And even those small impacts can be dangerous, like that one in Peru in 2007 in Caracas. They found a crater that was 50 feet wide.
Yeah, that was interesting. At first, scientists, even Peter Schultz, they were surprised by how big the crater was.
I mean, how big was the asteroid?
Well, they think it was only about 3 to 6 feet across. It's kind of amazing that something that small made it through the atmosphere and caused that much damage. It just shows that we need to take even the small ones seriously.
Okay, well, let's shift gears a bit. We've been talking about the dangers from above, but what about the forces shaping the Earth from within? Let's talk about the Great Lakes. They're huge, and they're incredibly important, for drinking water, for climate, for everything. So how did they form?
Yeah, the Great Lakes, they're amazing. Lake Superior, it's the deepest. Michigan and Huron, they provide drinking water for millions. And then there's Niagara Falls generating tons of power. So yeah, how did these massive lakes form?
Well, the research you sent points to this place called Kelly's Island on Lake Erie. There are these strange grooves carved into the bedrock.
Kelly's Island is a great place to start. Dr. Jeff Dick, he studied those grooves, trying to figure out what caused them. He ruled out volcanoes because there are fossils in the rock, and volcanoes would have been too hot for those to survive. And he ruled out water erosion because the grooves run the wrong way. perpendicular to the rock fractures.
So not volcanoes or water.
Right. What caused those grooves and ultimately carved out the Great Lakes basins was ice. And the research compares this to a glacier in Iceland called Vatnajökull, the biggest ice sheet in Europe.
And that thing is moving, right?
Yeah, it moves up to 3 feet per day, and the pressure it exerts on the land is just, I mean, it's massive.
Okay.
So picture this glacier, and it's full of rocks, and it's called dirty ice. And as it moves, it grinds away at the rock like sandpaper.
Wow. So like sandpaper on a massive scale.
Exactly. And there's evidence of this all over the Great Lakes region. You've got erratic boulders, these big rocks that don't belong. They were carried by the ice. And on Kelly's Island, there are fossils that indicate the water used to be a lot colder, back when the glaciers were there.
And the culprit, or I guess the sculptor, is the Laurentide ice sheet, right?
It was up to 2 miles thick and covered most of Canada and a big part of the U.S. for like over 1 million years. And as it advanced and retreated, it carved out these basins.
And that's how the Great Lakes formed.
Well, that's a big part of the story. There's also evidence that there were these faster-moving parts within the ice sheet, almost like rivers of ice. These fast ice areas, they could have carved out the long, thin lake basins more quickly.
And how quickly are we talking?
Maybe 100,000 years?
Mm-hmm.
So yeah, the ice carved out the basins, but then the big question is, when did they fill up with water?
And the research points to this bog, Willoughby Bog, between Lake Erie and Ontario. Francine McCarthy, she analyzed sediment cores from there. And she found evidence of water being there at least 9,000 years ago. And underneath that, there's this older layer, no signs of life, which is probably what those early lakes were like.
Yeah, those early lakes were probably really cold, full of sediment, not exactly a great place to swim. And, dating those early periods is tough because there's not a lot of organic material. But Niagara Falls, those can actually help us date the lakes.
Yeah, how?
Well, the falls are eroding, right? Right now, it's about half an inch a month, and it used to be faster. And as they erode, they move upstream. It's like a giant clock.
So by knowing how fast they erode, we can figure out when they started.
Exactly. And by dating clamshells found along the Niagara Gorge, Francine McCarthy figured out that the falls started around 12,600 years ago. So that's when the ice retreated from the Niagara Escarpment and water started flowing between Lake Erie and Ontario.
Wow, that's pretty cool. So that's the lower lakes. But the story of how they drained is pretty interesting too. I mean, today they drain east into the Atlantic. But it wasn't always like that, right?
No, actually. There's evidence that at some point they drained south through the Mississippi River into the Gulf of Mexico. And it makes sense. The Laurentide was melting, tons of water, and it would have found the easiest path.
But then something changed that, right?
Yeah, about 12,900 years ago, something caused them to switch to an eastward drainage. And one theory is that a comet hit the Earth around that time.
A comet?
Yeah. Alan West, he's a researcher who proposes this, and he's found some evidence, like carbon specks that could be from forest fires, microscopic diamonds, iridium, stuff you find in comets.
So a comet hit, and how did that change the drainage?
Well, the impact would have caused massive wildfires, maybe melted a lot of the ice sheet, and that could have, blocked the southward drainage. So Lake Ontario filled up, eventually burst through its eastern bank, and created the St. Lawrence River, and that's how they started draining east.
Wow. And there's a crater at the bottom of Lake Ontario, right? Could that be from the comet?
Maybe. It's about half a mile wide, but it hasn't been dated. It's possible that if the comet was mostly ice, it might not have left much of a trace.
And what about the upper lakes? Did they form at the same time?
Well, Francine McCarthy's research suggests they had slightly different histories, but they eventually connected. There's evidence that wild rice, which needs like big turbulent water, it started growing in Lake Erie around 4,230 years ago. And that probably means that Lake Huron, which was higher at the time, overflowed into Erie. And then the St. Clair River opened up, connecting all 5 lakes.
So that's how they became the Great Lakes we know today. And they're still changing, right?
Oh, yeah. The whole region is tilting.
Tilting.
Yeah. The north is rising, and the south is sinking. It's happening slowly, but it's measurable.
How do we know that?
Well, Professor Doug Hunter, he's a diver, and he found these ancient tree stumps in Lake Huron. They're submerged now, but they used to be on land. And by carbon dating them, we know they're between 6,400 and 7,900 years old. So Lake Huron used to be much smaller. It's risen over time. And then there's Mike Kramer. He uses GPS to track this tilting. He's found that the north is rising by about 1 inch per decade, and the south is sinking at the same rate.
So what's causing that? Why is it tilting?
It's called Post-Glacial Rebound. The Laurentide ice sheet, it was so heavy that it pushed down the Earth's crust. And now that the ice is gone, the land is slowly springing back up. It's like imagine pushing your finger into a cake, and then taking it away, the cake slowly rises back up.
So that's still happening today.
Yeah, it's a process that takes thousands of years.
It's amazing to think about all these forces, these asteroid impacts, these massive ice sheets, how they've shaped our world, and it's all still happening just on timescales we don't usually think about.
It really highlights the interconnectedness of everything. You've got asteroids potentially changing how the Great Lakes drain, the power of ice carving out these huge basins, and even today, the Earth's crust is still rebounding. It's a planet in constant motion, changing on so many different levels.
Well, that's a lot to think about. So to sum up, Earth is this dynamic place constantly being shaped by these forces, both sudden and slow. The stories of asteroid impacts and the formation of the Great Lakes are just two examples of this ongoing change.
And, as you go about your day, think about the vastness of time, the power of these forces. What other slow, subtle changes are happening right now, shaping the world around us, shaping our future? It's a pretty amazing thing to contemplate.
It's a genius with a twist where knowledge gets a remix. Brain power boost, no time for tricks. We take for your ordinary, the stuff you think you know. Flip it upside down, watch the knowledge grow. From history's hidden corners to science's grand design. We're uncovering secrets, one line at a time. Think you know about gravity? We'll show you how it bends. Think you master time? Prepare for unexpected ends. We're breaking down complex stuff, making it clear and bright. So grab your thinking caps, we're taking flight. A genius with a twist, yeah, that's the name. Education with a bang, it's not the same old game. We're twisting perspectives, turning concepts round. Knowledge explosion, the best sound in town. A genius with a twist, can you break the code? Before the video ends, the answer's bestowed. We use analogies, stories, and formats so fresh. No boring lectures, we're serving up knowledge with finesse. From ancient inventions to future tech so bright. We're connecting the dots, shining a different light. While butterflies winging inspires a solar array. Or how a simple echo can light up your day. We speak in real science, history too is true. But with a twist of humor, just for you. We show how genius thinking, innovation's bold. Impact every single day, stories to be told. From the smallest microchip to the stars up high. We're exploring the universe, asking why? But remember, there's always a twist, a surprise in store. Something you never expected knocking at your door. A genius with a twist, yeah, that's the name. Education with a bang, it's not the same old game. We're twisting perspectives, turning concepts round. Knowledge explosion, the best sound in town. A genius with a twist, can you break the code? Before the video ends, the answer's bestowed. So hit the like, smash subscribe, and join the fun. With a genius with a twist, the learning's never done. Stay curious, stay twisted, and don't forget. Shocking fact whispered quickly. Now go suggest some topic, what should we twist next? Can you solve this question before the end? If you dare, drop your guesses in the chat. A genius with a twist, stay twisted.